Good afternoon, everyone. Thank you for being here. I think a lot of you have seen this presentation already. I changed it a little bit, but for the ones that haven't, it's a pleasure to present you what I have been working for the last 3 years, almost. So the title of my research is the determination of solubility constants and thermodynamic variables for uranyl arsenate solids containing monovalent cations, sodium and potassium. This is something that I just learned and I wanted to share it with you as an elevated pitch. I got this from a workshop for faculty to be options, like to become a faculty professor. And they said, the moment that you present a short, your research short presentation, you have to do something that make people remember you. So I see my research as kind of an Alka-Seltzer when you're hungover, or as a bath bomb after wild camping. So I want to know how fast or how these uranyl arsenates can dissolve in water. So that's what the first thing that I thought was this. Now, going to the science specifically, first of all, if you see the map to the left, we have the US map specifically talking about Navajo Nation, because in this area, in our research group, we have found that there are very high concentrations of uranium and arsenic that exceed the maximum contaminant levels that the EPA allows. And actually, in all southwestern US, we have more than 500 abandoned uranium mine sites. So this is the motivation why I started to work on this research. So because of this large distribution of uranium and arsenic in these areas, specifically New Mexico and Arizona, we know that there is an ecological and human health risk from mining in Native American communities. We're talking about 20 times fold in uranium concentrations and 3 times fold arsenic. And the remediation definitely will cost billions of dollars. So here to the left, this is a graph that I made. Here you can see in water these high concentrations of uranium and arsenic. And I want to know what is the interaction between uranium and arsenic, and not only between the two of them, but also with other cations like sodium, like potassium, and eventually it could be with calcium, with phosphate. So when we have this information, we start looking for what are the other thermodynamic measurements that we have. And when we did that, I couldn't find much. So definitely there's no solubility product or any other thermodynamic variables related to uranyl arsenates. And that's when my research started. And eventually we might know how fast this dissolution occurs and as a function of pH. So these will provide a novel thermodynamic information from these synthetic materials for reactive transport models to interpret and predict uranium and arsenic solubility in environmental systems. So how I have been doing it? The first step is to synthesize a pure solid, or as pure as we can get, using a diffusion method. I synthesize 2 solids, the sodium uranyl arsenate, NaUAS, and potassium uranyl arsenate, KUAS. I used several characterization methods to make sure that we have these synthetic minerals, and especially about the stoichiometry. So after I did that, I started with solubility experiments, and I did 2 solubility experiments. The first one, I called it undersaturated experiments. That is basically the uranyl arsenate plus water, and put it in the rotator and leave it for 31 days. And then the supersaturated experiments are the uranyl arsenate, the DI water, and the salts that I call also stock solutions that are made up of the same elements that I use to synthesize the mineral. Then, after I get these concentrations, well, here actually to the right, we have this graph where in the X label, you can see the time that I reacted the solids, and in the Y axis, I have the concentration in moles per kilogram. And here you can see the elements that I measure in the ICP. So with these concentrations, I took them to pFlowtran, and I use these thermodynamic relations. So here, the Cj that you can see is the concentration, the activity coefficient, the stoichiometry coefficient, and also the activity of the mineral. And I get my KSP, my solubility product. Then I also use the enthalpy of formation. And this enthalpy of formation, I got it from a high temperature oxide melt calorimeter. So with these two measurements, I can get the relation to get the free Gibbs energy of reaction. And with the free Gibbs energy of reaction, I can get the free Gibbs energy of formation. And with the enthalpy, I can get the entropy of formation. So that's how I get all these thermodynamic variables. And so far, these are the results. Here,
sorry to interrupt, Isabel, that's 5.5 minutes, just so you know.
Oh my goodness, okay, that's it. So here are the results. And so far, my hypothesis has been proved so far, that I think that the solubility product and the thermodynamic measurements are pretty similar between these two different uranyl arsenates. And hopefully these solubility and thermodynamic variables obtained will be used in reactive transport models. I still have to do supersaturated solubility experiments for the potassium uranyl arsenate, and I will do exactly the same for a pH 4. And that's it. Thank you very much for your attention. And we go to questions now or at the end? No, okay.
You can take questions now, yeah.
I can take questions now. Thank you.
Yeah. All right, great job, Isabel. Does anybody have a question?
I have a quick question for you, Isabel.
Yes.
Very cool, very complicated work. You obviously did a whole bunch of experiments, I assume. Did you get much, and you're measuring these parameters, did you get much variation in your, when you measure this, like plus or minus 10%, plus or minus 100%? I don't know. That's the question I have with this.
You are totally right. I did not present the standard deviations of my results. I did in triplicates. So I got a standard deviation of 0.01, 0.02, so very low. So definitely, I think that statistically, I have confidence of the results. Even though I'm still working in the supersaturated experiments, let's see what are the results of those, and then I will do a statistical analysis of all the results that I get at the end. So thank you, Aurel. It's a very good question. I didn't know
very
that.
Cool. I'm jealous that you get results like that because it sounds fantastic.
Thank you.
All right. Any more questions?
I'll chime in. I can chime in.
Yeah, go for it.
All right. So this is awesome. Quick question. So now that you have solubility product information, how can scientists use this to make predictions about what's happening in the environment?
That's a very, very good question. So before I knew that if there was or not information about these uranyl arsenates, that was the first thing that I did in MinTech. In Visual MinTech. So when you put the different concentrations of elements, in this case of uranium and arsenic, I wanted to see when I get precipitation, right? With X amount of concentration. And I couldn't find it. So that is what I really want to do. I want that next person that needs to know when we will have a precipitate, having these two heavy metals, when we will have it, they will be able, anybody will be able. So hopefully these numbers will be put in databases like MinTech, like pFlowtran, like Minikil, and then we can have this information. Did I answer the
Now you
question?
got to call up Mintech and tell them you have these values.
That would be such a happy moment.